What's up guys, in this video I'm going to continue with the solution of some popular inorganic chemistry questions. As usual, I'm going to display the question and give a little explanation of the topic, then answer the question. Remember, if you have any question that have to do with the course, drop it in the comment box down below. So let's jump into it. Right, the first question, question 1a, says that differentiate between bonding and non-bonding molecular orbitals. Diagram is necessary. The question now is, what is the molecular orbitals? Molecular orbitals are actually formed due to the combination of individual atomic orbitals. So two orbitals will contribute electrons in order to form a molecular orbital, and that molecular orbital is actually the orbital of that new molecule formed. So for better understanding, I'm going to use a simple molecule, a hydrogen gas, which is formed due to the combination of two hydrogen atoms which possesses lone pair of electrons. A simple way to understand it is when these hydrogen atoms with their orbitals comes together, they overlap and they form a bigger orbital, right? Using the energy diagram now, these hydrogen atoms may find themselves somewhere at the middle. They are having equal energy, not high, not low. They are not sad and they are not happy. So this is the 1s, right? So I'm going to use human beings as an example. For example, a guy that is single, not in relationship, meeting a lady that is also single and not in relationship. Whenever these two humans meet, two things might occur. They may end up being in love, marrying each other, and having a happy home, happy family. But in this case, let's use anger as a higher energy. Or they may end up together but not being happy. So can you see the difference between this lower energy and this higher energy? These ones are happy, they are stable, while these ones are not happy and are always having contrary views. So now, since this one here, they are not in good terms, there is always a barrier between them. It's also applicable to whenever these hydrogen atoms combine with each other, they may either form what we call the bonding, the lower energy bonding, which is also the sigma bond, lower energy bonding, to form the hydrogen molecule, or they might be excited, having higher energy to form antibonding. This is the antibonding with sigma. So whenever they form a bonding, remember we said that this hydrogen here will overlap, right? And they form a bigger orbital. But whenever they have higher energy, what do you think will happen? This is one of the hydrogen and this is one of them. Remember that these ones here have a barrier, they have a knot, right? This one is opposing this and this one is also opposing this. So this is the kind of orbital you have. There is always a knot here. So it's virtually applicable to the molecules or the atoms. When they combine, they either form a lower energy sigma bond or they form a higher antibonding molecular orbital. So with this explanation, let's now answer our question. Alright, with a little understanding we've gained about the analogy, the question says we have to use diagram, right? So we're going to use hydrogen atom as an example again. As we know, we have the hydrogen atom here, which is having 1s coming together with another hydrogen atom, which is having another 1s, right? So this is the atomic orbital. This one too, orbital. So this one is having a lone pair of electrons. This one is also having a lone pair of electrons. As we've seen from our explanation, that these hydrogen atoms will prefer to start filling in these lower energy sigma orbital. This one contribute one electron. and the other one contribute an electron, we have something like this, right? Then the next one at the top, which might not be filled up, is the antibonding. Antibonding sigma molecular orbital. So this one here, these ones are the atomic orbitals. This one now will be the molecular orbital. This contribute from here and this contribute from here. Having this one here is empty, but when these electrons say are higher in energy, as we've seen, they may tend to jump to the anti-bonding, because the anti-bonding usually signifies higher energy. So that's our diagram. Then let's differentiate the bonding from the anti-bonding proper using a tabular form. So with our explanation and the diagram now, let's finally differentiate between bonding and anti-bonding molecular orbital. As we know that the bonding will always have less energy because they are always stable. So we say the first difference is that has less energy when you compare it to the parent atomic orbital. While this one will have higher energy, right? We've seen that those, as we've said, that the anti-bonding will always have higher energy compared to the parent atomic orbital. Number two, as we've said that the bonding is always stable compared to the anti-bonding. So we say stable. It's even stable than the parent atomic orbital. The anti-bonding now is always unstable, right? The fourth thing we should notice is that the electrons will always prefer to stay in the bonding, right? So there is high possibility of getting electron or high probability of finding an electron, right? So electron, while this is always low probability. Then the last thing to note here is that this bonding will always contribute towards the shape of the molecule. So we say, why? We've said that when the hydrogen, as we've said, when the hydrogen ion comes with the other hydrogen ion, they always form a bigger orbital, right? But remember, we say when it is anti-bonding, when they come, they repel against each other, they always form a knot between them. So the bonding will always contribute to the shape of the molecule, while the anti-bonding will not. So we say it does not contribute. So basically, these are some of the differences between bonding molecular orbitals and non-bonding molecular orbitals. So let's go to the next question. Alright, the second part of the first question, that's question 1b, says write the molecular orbital configuration of nitrogen molecule and nitric oxide, calculate their bond order, and predict the magnetic behavior. So this question is the application of the number 1a. So how we're going to approach it? As we are aware that the molecular orbital is a combination of the atomic orbital forming the bonding, the anti-bonding molecular orbitals. So before doing this, you have to know the electronic configuration of that atom. After writing the electronic configuration now, then we will be able to know how we are going to assign those electrons. So let's try it and see. So starting with nitrogen molecule, which is formed by the combination of two nitrogen atoms. I know that the atomic number of nitrogen is 7. So we said the nitrogen atom always have the atomic number of 7. The electronic configuration will be 1s2, 2s2, and 2p3. So each of these atoms have this atomic configuration, electronic configuration. So let's draw the molecular orbital diagram and see the energy. So So as we know, on this side we have one of the nitrogen atomic orbital, and the other we have the other nitrogen atomic orbital. So this one is the what we need to do is that we are not going to include this 1s. So we're going to start from 2s, right? So we have the 2s here, and we have the px, py, and pz. Px, py, and pz. So this is 2s, then we have px. The first one here will be the molecular orbital, right? The molecular orbital. And as we know that there are 2 electrons here, then we have singly, enter singly. It's not a magic. These electrons are coming from this electronic configuration. So remember, we have 2 electrons in the 2s. Can you see them here? Then we have 3 electrons in the p orbital, which are these. See them here. So don't be confused. Now, in forming the molecular orbital, now these ones will now contribute electrons, leading to the formation of sigma bond here and anti-sigma bond here. So this one will contribute one electron from here and from here. Remain one, then remain one. So they will put them here, making 4. Then for this one here, we know that there are 3 orbitals from each of them, the px, py, and pz. In this case now, we are going to have a pi and a sigma bond. So we have 2 pi bonds here, right? So this is the pi px, and we have the pi py. Then we have the sigma pz, right? Then at the top here, we have the anti-x, and as you say, anti pi py. Then at the top we have the sigma anti-sigma pz. So now this atom will contribute 1 electron here and electron here, so giving us something like this, and like this, right? Remember how many? Remember 1. So we have something like this. So none of these anti-bonding or anti-molecular orbital will be filled, right? So this is the molecular orbital of nitrogen molecule. So this is the nitrogen molecule. So writing the molecular orbital electronic configuration of nitrogen molecule will be, we start with this, which is 2s sigma. There are 2 electrons there. Then followed by this, which is also 2s anti-sigma orbital. There are 2 there. Then we have this, which is pi px, and there are 2 electrons there. Then we have this, which is pi py, and there are 2. Then lastly we have this, right, which is sigma pz, and there are 2. So this is the molecular orbital electronic configuration of nitrogen molecule. So the next thing is to calculate the bond order of the nitrogen molecule, and bond order is given as bonding molecular orbital minus the anti-bonding molecular orbital divided by 2. So counting the electrons in the bonding molecular orbitals, we have 2, we have 4, we have 6, and we have 8. Remember that the bonding molecular orbital doesn't have asterisks on them. They don't have star, right? It's only the bonding that have star. So we have 8 electrons there. So we say 8 minus, now anti-bonding we have this only, that's 2. So minus 2 divided by 2 is going to give us 8 minus 2 is 6 divided by 2. So our bond order now, 2 here is 1, 2 here is 3. Our bond order is 3. That's why nitrogen is having 3 bonds, right? So that's the bond order of nitrogen molecule. So the next thing is for us to predict the magnetic nature of the molecule, because the question says we should predict its magnetic behavior. So what's the magnetic behavior of nitrogen molecule? Is there any unpaired electron? All the electrons, we can see that they are paired up. If we were having an unpaired electron, we will say yes, then it will be paramagnetic. But since there is no unpaired electron, we say that what the magnetic nature is, say magnetic nature or behavior is what diamagnetic. Is diamagnetic simply because there is no unpaired electrons. So all the electrons are paired. So that is it for nitrogen molecule. Let's go to the next molecule. Alright, the next molecule is nitric oxide. So the next molecule we have here is the nitric oxide, which is formed due to the combination of nitrogen and oxygen atoms, right? So we have to know the atomic number of nitrogen and that of oxygen and write the electronic configuration. As you know that nitrogen is number 7, so we said nitrogen 7 is 1s2, 2s2 and 2p3, right? Then oxygen is number 8, 1s2, 2s2 and 2p4. So these are the electronic configuration of the atom we're going to use. One here, the atomic orbital of nitrogen, while this side, the atomic orbital of oxygen. Remember that we're going to omit the 1s, we don't need it. So in this case, we have the px. Nitrogen is having 1, 2, that's 2s. Then we have 3 electrons in the p orbital. See them here? 1, 2, 3. Out of oxygen. Oxygen, as you can see, is having 2 electrons here. We have 1, 2, then 4 electrons in the p orbital. So that means we're going to enter singly 1, 2, 3, then 4. So these are the atomic orbitals. So drawing the molecular orbital now for the molecule, as we know that this nitrogen will contribute 1 electron, two electrons, one from the oxygen and one from the nitrogen. Then we'll have the antibonding 2s, so making the total of 4 electrons, 2 here and 2 here, making the total of 4 electrons, right? So we have the 4 electrons here. So then for the p orbital now, as you know that there is pi bond here, so we are going to do it in this way. So, and at the top, as we know that there is antibonding molecular orbital, so we will have the antibonding pi. So drawing the electrons now, we know that it's going to contribute, this one here is going to contribute electrons. We have one here and another one here. Then this one too will contribute. We have this and this. So making 4 electrons, right? And finally this one will contribute 1. For this one now, it has made its total contribution. Then this one here is going to contribute 1 electron here, right? So remember that this one have made its total contribution. This one have made its total contribution of 3 electrons. So this one is left with 1 electron. So it will jump here. So this is the molecular orbital diagram for nitrogen oxide or nitric oxide. So now the molecular orbital electronic configuration will be, we have sigma 2s, can you see 2? Then we have the sigma anti-bonding 2s and it's having 2. And finally, we have the pi anti-bonding 2px, and there is only one electron there. So this is the molecular orbital electronic configuration. We have sigma 2s, we have 2 electrons there. Then sigma anti-bonding 2s, 2 electrons there. Then we have pi 2px, 2 electrons, and we have pi 2py, 2 electrons, sigma 2pz, 2 electrons, anti-bonding pi 2px, and there's only about 1 electron there. So calculating the bond order now, as we said, bond order is given as bonding molecular orbital minus anti-bonding molecular orbital divided by 2. So now let's count the bonding molecular orbitals. We have this 1, 2, 3, 4. These are the 4 orbitals, and each of them have 2 electrons. So that's 8 electrons. We're going to say. So let's count the number of electrons in the bonding molecular orbitals. As we know that the bonding orbitals are those orbitals without asterisks, and those anti-bonding are those orbitals with asterisks, right, with star. So we have the bonding molecular orbitals are, we have 1 with 2 electrons, 4, 6, and 8. So there are 8 electrons in the bonding molecular orbital. So we say 8 minus, then the anti-bonding molecular orbitals, we have 2 and we have 1, making 3, right? So say 3 divided by 2 is going to be 8 minus 3 is 5. Divided by 2 is equals to 2.5. So this is the bond order, right? And finally, for this question, what is the magnetic nature? The magnetic nature. As you know, we can predict the magnetic nature of the molecule. Remember, we have 1 unpaired electron here, and this will result to paramagnetism, since paramagnetism have to do with unpaired electrons. So we have this one will be what? Paramagnetic. So that's all for the question. Let's check the next question. Right, the second question is to explain the principle of the Chelate effect and what is the major thermodynamic parameter responsible for this effect. So there are 2 questions here. The first question is to explain the principle of Chelate effect, and the second part is to mention the thermodynamic parameter that is responsible for the Chelate effect. So let's check it out. Alright, to explain this Chelate effect, we have to understand the various types. Alright, to explain this Chelate effect, we have to know the types of ligands. As we know, we have monodentate ligands, these monodentate ligands always have 1 point of attachment to the central metal. Have 1 point of attachment, while we have the polydentate ligands, and these polydentate ligands have 2 or more points of attachment to the central metal, or we can say they have several points of attachment to the central metal. The polydentate ligands, right? Multiple point of attachment. multiple point of attachment. So this chelate effect have to do with these polydentate ligands. So in another word, we can call these polydentate ligands chelating ligands. These chelating ligands have higher affinity for a metal ion than the monodentate ligands, and that makes them very, very stable. They have strong passion for the metal ions, the central metal ions. They have passion for it. They have strong affinity for the metal ion than the monodentate ligands. In other words, the chelate effect is the enhanced affinity of a chelating ligand for metal ion compared to the monodentate ligand. So that's the principle. The principle here is that these chelating ligands have higher affinity for the metal ions compared to the monodentate ligands, and as a result of that, it makes them more stable than the monodentate ligands, right? Now, this chelate from this word chelate is derived from a Greek word called chela or chela, anyone you call it, which means cloud or crab. So let's see an example. All right, using this picture as an example, you can see two crabs here holding on to a copper metal. One thing you should note here is that a crab does not have any teeth at all, but it does have two claws for tightly holding onto something for a couple of reasons. A very simple analogy is that if you are holding something with two hands rather than one, you are not as likely to drop. Why? Because you are holding it with two hands, right? So also the polydentate ligands. The polydentate ligands are having several points of attachment to the central metal, therefore making them more stable and holding the metal most tightly and strong. So for example, now the bidentate ligands, which is also a polydentate ligand, the bidentate ligand bind through two donor sites, right? They bind through two donor sites, and bidentate means two-toothed. A very good example of a bidentate or a polydentate ligand is the ethylene diamine, which have something like this. So this ligand can attach through this nitrogen to the central metal and also through this nitrogen. So you can see that it has 2 points of attachment because it has high affinity for this metal ion. So comparing these to a monodentate ligand, this one will be more stable compared to this. So finally, the principle of the chelate effect states that these chelating ligands have strong affinity for the central metal ion compared to the monodentate ligands, which makes them more stable, right? So that is the principle of the chelating ligand. Then the second part of the question states that what is the major thermodynamic parameter responsible for this effect? There are basically two parameters, and these parameters are enthalpy and entropy. As you know that enthalpy is the total content, as you know that enthalpy is the total heat content of a system, or the internal energy of a system plus the product of pressure and volume. So this is total internal heat content, total heat content of a system, while entropy is actually the degree of disorderliness of a system. So these are the major thermodynamic parameters responsible for this chelate effect. The question is how. So in terms of enthalpy, in order to explain this, I'm going to use two examples, two complexes. One is monodentate and the other one is bidentate. So we have ethylene diamine connected to this central metal. Then we also have a monodentate ligand. Right. In terms of enthalpy, in order to completely remove a bidentate ligand, two coordinate bonds must be broken. So as we are aware that this bidentate ligand is connected through two places, right? In order to remove this ligand, you have to break two bonds, comparing to breaking this monodentate ligand, which is always a single point of attachment. So breaking bidentate ligand, it will cost you more energy because you have two bonds to break, compared to breaking a monodentate ligand. Only one bond you have to break. So breaking this bidentate ligand, it will cost more energy compared to breaking a monodentate ligand. So that's the first parameter that is responsible for this chelate effect, enthalpy. Okay, as we said, the second thermodynamic parameter responsible for this chelate effect is entropy. And I'm going to use the same example I used in enthalpy. Now, in terms of entropy, which deals with the distribution of energy within a system, it is generally thought that bringing two molecules. So can you see this is ethylene diamine, that's one molecule, plus this metal, that's two. So bringing two molecules will cost less energy compared to bringing three molecules. Can you see 1, 2, and 3? This one is three molecules. So bringing two molecules will cost less energy compared to bringing three molecules together. That's because individual molecules are free moving around, tumble and vibrate independently. Once they come together, they have to do all these things together. So on a nutshell, for proper understanding, you should know that bringing this ethylene diamine together with this metal will cost less energy compared to bringing these two molecules together with this metal. So this is only two entities, and this one is three entities. So energy will be less here. So it's more easier to bring these two molecules than to bring these three molecules together. This energy will be more. So that's the explanation with entropy. All right, the third question we have here is to differentiate between the effective atomic number rule and the 18 electron rule. So I'm going to explain the effective atomic number rule and the 18 electron rule. Then we will differentiate them. So the effective atomic number rule, which is also known as the EAN, said that in a number of metal complex, the metal atom tends to surround itself with sufficient ligands that resulting to effective atomic number is numerically equal to the atomic number of the equal noble gas element found in the same period in which the metal is situated. So in other words, we can say that the effective atomic number describes that the metal atom has to obtain the electronic configuration of the noble gas present in the same period to become stable. So to explain this better, it is said that this EAN is equals to Z minus X plus Y. So what is this Z and X? What is this Z, X, and Y? This Z is equals to the atomic number of the central metal. Then the X is the oxidation state of the central metal. And lastly, the Y is the number of electrons donated by the ligands. So that's the formula for calculating the effective atomic number of a complex. Remember that this rule have to do with the stability of that complex. So on the nutshell, it's trying to explain that the center metal must have ligands that after calculating the atomic number, it should be equal to that of the noble gas that is on the same period, as in the same period with the metal, equal to noble gas, right? On the same period of the metal. So we're going to use this formula to calculate the effective atomic number of a certain complex to see whether it is going to obey it or not. So I'm going to use this complex to explain this effective atomic number rule. So we have nickel, carbonyl ligand as a ligand 4. So the first thing to do is to calculate the oxidation state of the central metal, which is nickel. We have X. Remember that the oxidation state of the central metal is usually given as this X, right? So we can say that X now is equal to 0. Then what is the atomic number of the central metal? The atomic number of nickel is 28. And finally, the number of electrons donated by the ligands. So remember, we have 4 of the carbonyl. Remember, we have 4 of the carbonyl, and each one usually donates 2 electrons, right? So we can say 4 times 2 is equal to 8. So this is the number of electrons that will be donated, and that is our Y. That is our Y. 8 electrons. So applying the formula, we know that minus what is our X, 0, plus our Y is 8. So 28 plus 8 is equals to 36. So let's check the periodic table. To see the position of nickel, that is the center metal here, and that element that have this 36, the atomic number of 36. If it's a noble gas, then that means it satisfies the effective atomic number rule. So this is nickel is number 28, and after the calculation we found out that we got 36, which is actually this krypton, and krypton is a noble gas. That means that complex satisfied the effective atomic number rule. Why? Because after the calculation, and the atomic number is equal to that of a noble gas in that period. Can you see this is nickel? Is in the same period with this noble gas krypton, right? We'll now say that this satisfies the effective atomic number rule. Alright, on the other hand, the 18 electron rule, which states that the thermodynamically stable transition metal compounds contains 18 valence electrons, comprising that of the metal d electrons plus the electrons supplied by the ligands. So on the nutshell, we said that the d orbital electrons of the metal plus the electrons supplied by the ligand should give us the total of 18 electrons. That's what the 18 electron rule. And the 18 electron rule was proposed to explain the stability of transition metal and organometallic compounds which they form. So in this case, the 18 electron rule, on the other hand, states that the thermodynamically stable transition metal compounds contain 18 valence electrons, comprising that of the metal d orbital plus the electrons supplied by the metal ligands. So now, to make it short, is simply saying that the electrons, the d electrons of the metal plus the number of electrons supplied by the ligands should be equals to 18. So we should always have 18 electrons. That's the 18 electron rule. So let's see a very, very good example. But put it in mind that this 18 electron rule was proposed to explain the stability of transition metals and the organometallic compounds which they form. We have this cobalt. So the first thing to do here is to calculate the oxidation state of the central metal, which is our unknown. Now the electronic configuration of cobalt is equal to argon 3v7 4s2. Remember that it's going to lose 3 electrons from the oxidation state we've calculated. So removing 3 electrons, 2 from the 2s and 1 from this, right, making 3 electrons. So the new electronic configuration of cobalt now. So these are the numbers of these are the electrons in the d orbital. Remember that the 18 electron rule says that the electrons of the metal plus the electrons supplied by the ligands should be equals to 18. So we have that the d electrons here equals to 6. Then check the ligands. We have 6 ligands, right? We have 6 ligands, and the meaning of these 6 ligands is that they are going to donate pair of electrons. That means 6 times 2, since they are in pairs. So chlorine 6 will give us 6 times 2, making a total of 12. So if you add this plus this electron, so we have 6 plus 12, total of 18 electrons. So 18 electrons. So based on the 18 electron rule, this complex is stable because it's having the total of 18 electrons. So going back to our question now, what is then the key difference between the 18 electron rule and the effective atomic number rule? As we know that the 18 electron rules indicate that there have to be 18 valence electrons around the metal in the coordinate complex to become stable, and the effective atomic number rule describes that the metal atom has to obtain the electron configuration of a noble gas, right, present in the same period to become stable. So with this expansion, what's the key difference between the 18 electron rule and the effective atomic number rule? So the 18 electron rule, as we know, it states that that complex must have the total of 18 valence electrons after the addition of the d orbital electrons plus that of ligand. So we said there should be so in order for the complex to be stable, there should be 18 valence electrons, which is coming from the d orbitals plus those electrons donated by the ligands. And on the other hand, the effective atomic number rule describes that the atom has to obtain the electronic configuration of the noble gas present in the same period, right? So effective. So that's the basic difference. So the next question. All right, number 3b. The question states that on the basis of the effective atomic number rule, that's the EAN, predict the stability of the following complexes. We have 3 complexes here to predict whether they're going to be stable or not. Remember that the effective atomic number rule states that the complex must have the electronic configuration of a noble gas in that period, right, to be stable. So let's see it. We're going to use the formula that was provided in the previous uh, discussion to solve this. Alright, this is the first question, and we know that the formula for calculating the effective atomic number rule is where Z is the atomic number of the central metal. Then X is the oxidation state of the central metal. And lastly, Y is the electrons donated by the ligands. So the first thing to do here is to calculate the oxidation state of the central metal. So we know that nickel is, that means our X from the formula here is going to be equals to 0. Then the atomic number of nickel, in this case from the periodic table, the atomic number of nickel is 28, and Y is the electrons donated by ligands. Remember, we have 4 carbonyl, right? So each of them will donate 2 electrons because it's pair, it's always in pairs. So we're going to have 4 times 2, giving us a total of 8. So remember our formula, EAN is equals to Z minus X plus Y plus Y. So this one is going to be, our Z is 28 minus our X is 0 plus our y is 8. So 28 plus 8 is going to be 36. So let's check the periodic table whether there is whether this is the atomic number of a noble gas in the same period with nickel, right? So let's check it. All right, this is the periodic table, and this is nickel, right? Remember that our solution, we found out that the effective atomic number of this complex is 36. So, and on the periodic table, we check 36 is krypton, which is the same thing, which is equals to the noble, which is equals to the atomic number of a noble gas in the same period with nickel, right? This is the period 4, right? In period 4, nickel is in period 4, and krypton is the noble gas found in that period. After the calculation of our uh, effective atomic number, we found that is equal to the krypton. So we're going to say that this one obeys the effective atomic number rule and is going to be stable. So this is the next complex. As usual, let's calculate the oxidation state of the center metal, which is iron. So we know that potassium is positive 1. So that's the oxidation state of the central metal. And the atomic number of iron is on the periodic table. So remember our formula: effective atomic number is equals to our Z, which is the atomic number of iron, is 26. The X, which is the X, which is the oxidation state of the central metal, is plus 5, and Y, which is the number of electrons donated by ligands. We have 6 of the cyanide, so each of them donating a pair of electrons is going to be 6 times 2, giving us the total of 12. So we're going to say 26 minus 5 plus 12. So this is going to be 21 plus 12. The total here is 33. So that is the effective atomic number of this complex. So let's go back to the periodic table and check whether we have a noble gas that has this atomic number on the same period with the central metal, which is this iron. So iron is in period 4. Can you see it? And remember, our effective atomic number is 33. So let's check. Is there any? Of course, 33 on that period is arsenic, right? Arsenic is not a noble gas. So our conclusion here is that this one here will not be a stable complex. So not stable. So this is our last complex to check whether it will obey the effective atomic number rule or whether it will be stable. So as we know that iron, our formula, the effective atomic number rule is equals. So the atomic number of iron on the periodic table we know is 26. Then our X, which is the oxidation state of the central metal, is 0, and our Y, which is the number of electrons donated by the ligands, we have 5 of them. So our EAN is going to be number, right? So let's check the periodic table. If we have any noble gas that has 36 as its atomic number and is in the same period with this central metal iron. So as we can see, iron is in period 4, number 26. After the calculation of the effective atomic number, we got 36, right? Which is krypton and is a noble gas. That means this complex, it will be stable and it obeys the effective atomic number rule. So we say stable. So that's all for the question. All right, question 4a states that using simple manipulation, show that beta 4 is equal to K1, K2, K3, and K4, where K1, K2, K3, and K4 are the stepwise stability constant, and beta 4 is the overall stability for four coordinate system. So in order to solve this question, think of a complex that have four ligands, and these four ligands are added one ligand at a step, right? They added one ligand at a step. So that's what we are going to use now. So remember that we are going to form this complex, right? The first step is to react the metal plus the ligand. Metal and the ligand, right? But before we proceed, there is what we call equilibrium constant in every reaction in chemistry. This equilibrium constant, which is usually represented by K, and it is actually the concentration of the product all over, or divide by the concentration of individual reactants, right? So if you, for example, if you have a reaction A reacting with B to produce C, now the equilibrium constant now is going to be K equals to our product, the concentration of C, all over the concentration of the individual reactant, which is A and B, the concentration of B. So this is the equilibrium constant for this reaction. We're going to use that to our advantage to solve our problem. So now we have reacted a metal and a ligand, right, to produce this Ml. So the equilibrium constant here, this is for the first step, is going to be K1 is equals to, remember this is our product, we're going to say the concentration of the product, Ml, all over the concentration of the individual reactants, right? Then for the second step now, we're going to carry this same product to react it further with another ligand. So this will produce metal with two ligands. And the equilibrium constant here for the second step is going to be something like this. The third step, we are to carry this product to further react with the ligand. So we have, will give us now Ml3. So this step is going to be K3, right? Then the last step, since it is four coordinate system, we're going to carry the last product, which is Ml3, and react it with another ligand. Will produce Ml4. And in this case now, the equilibrium constant. So this is actually our product, right? Since it's now the same with this four coordinate system. So in this case, and these K1, K2, K3, and K4 are called the stepwise stability constant. K1, another way to call it is actually the stepwise formation constant. Why? Because these reactants are reacting to form a new product. So it is also called the stepwise formation constant. But there is, however, a different way of looking at this. Instead of reacting one ligand at a time to produce this product, there is another way of doing it. So we can act it like this. For the first step, we can use the metal plus a ligand, which is always a reversible reaction, and it will give us the metal and the ligand, right? Then instead for us to carry this and add it to another ligand to produce something like this, why can't we just add a metal plus two ligands to give us, can you see it's not the same, it's the same with this. So also, instead for us to carry this final product and add the ligands, we can just add them directly to be M plus now three ligands. So also the fourth one, And can you see it's also giving us the same product with this. In this case now, we're not going to call this equilibrium constant. We're going to use beta 1 here. So this beta 1 now is going to be the concentration of our product all over the concentration of our individual reactant, right? Then for the second step, that's beta 2. So you can see that this one, we have two ligands here. We are going to write it as the power of the concentration of that ligand. So it's power 2. Then for the third step, beta 3. Four. So this is beta 1, beta 2, beta 3, and beta 4 are called the overall stability constant. Since beta 1, beta 2, beta 3, and beta 4 leads to the formation of the same product with this, right? Since this K1 will lead to the formation of this product, and the product is the same thing as this product, then that means beta 1 is same thing as K1, beta 2 is same thing as K2. So even if we are going to continue getting them, it's going to be the same. So beta n is equals to Kn. That's infinity. So that's the relationship between the stepwise stability constant and the overall stability constant. All right. The second part of number 4, that's question 4b. It says that explain the Lanthanides contraction and what is the cause and consequences of the effect. We are to explain the Lanthanides contraction and state the cause and the consequences of the effect. As we are aware that lanthanides and actinides are the F block elements, right? They exhibit this property of contraction. But why? But before going into it, it would be nice if we understand the structure of the atom and how it behaves. We are aware that the atom is made up of a nucleus surrounded by electrons on the orbital, right? So there are electrons here. Now, there is always an electrostatic force between this nucleus and the electrons on the shell, which makes the electron to always be in shape, not to move out of the line. So that's why you find that the electron will always be circulating around the atom. So this electrostatic force, remember, is as a result of the positive charge protons inside the nucleus. And since the electron is negatively charged, there is always a force between the electron and the proton. Let's now talk about the Lanthanide contraction. So this Lanthanide contraction is actually the gradual decrease in the atomic and ionic size of the lanthanides with increase in atomic number. So we said so that's the definition. It's a gradual decrease in the atomic and ionic size of lanthanides with increase in atomic number. But how? Okay, now let's understand the atomic structure of these lanthanides. As we have seen earlier that every atom is made up of a nucleus. And this nucleus contains the protons and the neutrons. The protons are positively charged while the neutrons are neutral. And since the lanthanides are actually the F block elements, we're going to say the first shell now is the first shell. Let's assume is the S orbital. The next is the P. The next one is the D. And finally, we have the F. So let's assume this is the atomic structure of the lanthanides. Now, remember that there are electrons in this orbital. as we have seen that there is always an electrostatic force between this nucleus and the electrons, and that's why they are always in shape and always in their orbits, right? Okay, for this last orbital, what do you think is going to happen? One thing you should know that it is far away from the nucleus, and apart from that, there are electrons here on this shell, and apart from that, these shells, right before these shells, are actually shielding it from that electrostatic effect or electrostatic force. They are shielding it. Why? Because there are a lot of electrons. They are protecting it from this electrostatic effect. So the electrons in this shell now will not have much effect of this electrostatic force. Why? Because they are being protected by the electrons here. They are shielded. It is always difficult for electrostatic force to penetrate and be felt here. So the question then is, what if there is no shielding? There is no protection of this final orbital by these inner electrons or inner orbitals. What will happen? So imagine there's no shielding. Know that the electrostatic force will be felt by all the electrons on the Earth orbital, right? Thereby, it will force that orbital to come closer to the nucleus. So that is actually the basis of the lanthanide contraction. Since we said that is the gradual decrease in the atomic and ionic size of the lanthanides with increase in the atomic number. So the question is then, what is the cause of this lanthanide contraction? This contraction is actually as a result of a poor shielding effect of the 4f electrons, right? So the 4f electrons are no more protecting the electrons here. So thereby there is electrostatic force. There is strong electrostatic force from the nucleus to the electrons on the final shell, right? Thereby drawing them closer and squeezing the size of the lanthanide. So we say the cause of lanthanide contraction is as a result of poor shielding effect of the 4f electrons. 4f electrons. So the shielding effect is described as the phenomenon by which the inner shell electrons shield the outer shell electrons, as we have seen earlier. So they are not affected by a nuclear charge or by the electrostatic force, so-called electrostatic force, as we've said. So when the shielding is not good, this will mean that the positively charged nucleus has a greater attraction to the electrons, as we have said. It will now drag those electrons at the final shell closer to the nucleus. Think of your house when the door is open. You are likely to attract thieves, diseases, and all sorts of things. You'll be vulnerable, right? So that's a very good example of the lanthanide. That's what happened. Since there is no protection there's no shielding by the 4f electrons, then those electrons at the final shell will now have great effect of the electrostatic or the nuclear charge, thereby dragging the size or the electrons closer to the nucleus. So that is the cause of the lanthanide contraction, poor shielding effect of the 4f electrons. So finally in the question, we are to state the consequences of this lanthanide contraction. So what are the consequences? Of course, so one thing to note here is that the contraction describes the atomic reduced trend that the lanthanide series exhibit, right? Which will always determine their properties. So the important consequences of this lanthanide contraction is one, the atomic size. What happened to atomic size? As we have seen that the atomic size will always decrease. Due to this contraction, the size of the tri-positive lanthanide ion decreases regularly with increase in atomic number. So this lanthanide positive ion will always what? Decrease. Ionic size will decrease. So that's one of the consequences. The second consequence here is that it leads to the difficulty in the separation of the lanthanides. So since all the elements in that period will always have the same size, it will be hard for you to separate them. Another consequence of this contraction is that the basic strength of the hydroxide decreases from lanthanum hydroxide to lutetium hydroxide due to the contraction. So decrease in the basic strength of hydroxide from lanthanum hydroxide to lutetium hydroxide. The fourth consequence is that it increases the covalent character of the metal hydroxide bond. So these are some of the consequences of this lanthanide contraction. It decreases the atomic size, right, with increase in atomic number. Then it causes the difficulty in the separation of the lanthanides. Then the third one, we said it decreases the basic strength of the hydroxide from lanthanum hydroxide to lutetium hydroxide. Then finally, we say it increases the covalent character in the metal the metal hydroxide bond. So that's all for this question. So the fifth question here is outline the similarities and the differences between the lanthanides and the actinides series. The question is, what are lanthanides and actinides? The lanthanides and the actinides are the F block elements, and they occupy the lower or the bottom part of the periodic table. You can see that this part, the lower part of the periodic table, is made up of the lanthanide here, and we have the second lower part, the actinide. So they are actually those elements that occupy the lower part of the periodic table, and we call them the F block elements. So now going to our question, the similarities between these series. The first similarity here is that both the series elements mostly show an oxidation state of positive 3. The second similarity here is that both of these series are highly electropositive. Both of them are highly electropositive. Now the third similarity is that both of them are F block elements. Both of the series are F block elements. And another similarity is that there is what we call contraction, lanthanides and actinide contractions. So both of them shows contraction in their atomic radius or in their atomic radii, and they also show magnetic properties. So both of them shows contractions in their atomic radii, and they also show magnetic properties. So both. So these are the similarities between the lanthanides and the actinide series. So both shows oxidation state of positive 3, both are electropositive, both are F block elements, and both of the series shows contraction and magnetic properties. So let's check the differences. So what are the differences between these series? These two series, the fact that both of them are F block elements, they have differences. The first differences between the lanthanides and the actinides here is that the actinides can form complexes easily, while the lanthanides do not form complexes easily. So said the actinides form complexes easily while lanthanides don't. The second differences between the lanthanides and the actinides is that the actinides are mostly radioactive elements, while the lanthanides are mostly non-radioactive elements except promethium. Are not. The third difference is that most actinides ions are colored, while most lanthanides ions are colorless. Most actinides ions are colored, while most lanthanides ions are colorless. Right? The last differences between the lanthanides and the actinides series is that the actinides are 5f orbital electrons while the lanthanides are 4f orbital elements. All of them are f block elements as we've seen, but the actinides are 5f orbital elements while the lanthanides are 4f orbital elements. So these are basically the differences between lanthanides and the actinides. There are a lot of differences. One thing you should know is that the actinides form complexes easily while the lanthanides don't form complexes easily. The actinides are mostly radioactive while the lanthanides are mostly not. Most actinide ions are colored while the lanthanide ions are colorless. Then the actinides are the 5 orbital elements while the lanthanides are the 4f orbital elements. So that's the difference. Alright, number 5b says differentiate between the spectrochemical series and the Nephelauxetic series. But to differentiate between the spectrochemical series and the Nephelauxetic series. Alright, the spectrochemical series is the arrangement of ligands based on the order of splitting ability and also the arrangement of metal ions based on oxidation number. So, as we said, this spectrochemical series actually arranges these ligands based on their splitting ability. As we know that when ligands approach the central metal, there is repulsion between the ligand's electrons and the metal electrons, therefore causing splitting based on the crystal field theory. So these ligands, there are ligands that will cause higher splitting, while there are ligands that will usually cause lower splitting. So this spectrochemical series actually arrange those ligands based on their splitting ability, and it also arrange metal ions based on their oxidation state. So this is the spectrochemical series. You can see that they are actually arranged based on their splitting ability, right? So the ligand that will always have the lowest splitting ability is iodine, right? And the ligand that will always have higher splitting ability is this carbonyl. Can you see? So they actually arrange these ligands based on their splitting ability. It also involves the arrangement of metal based on their oxidation state. On the other hand, is the Nephelauxetic series. Now, what is this Nephelauxetic series? The Nephelauxetic series is actually the arrangement of ligands and metal ions according to their Nephelauxetic effect. Nephelauxetic effect. This term Nephelauxetic is derived from a Greek word which means cloud expansion. Cloud expansion. And so it is believed that when these ligands combine with the metal, it increases the stability of that complex compared to when the metal is in its free state. How? Let me use an example here. So as we know that the d orbital is always in this form, as you know, this is the diagram of the metal d orbital, and as a result of that, these d orbitals, since they are closer to each other, there's always a repulsion between the orbitals. Remember that in those orbitals there are electrons, so those electrons will always be repelling against each other, and this is when the metal is in its free state, where we said free metal ion. metal ion, and as a result of that, it makes the entire metal to be unstable due to the combination of the metallic and the ligand orbital. These orbitals will now expand. It will become bigger because it is no more only the metal, it is a combination of both the metal and the ligand. So we have something like this. So from this one here, since it's a combination of both the metallic and the ligand orbital, you can see that we are now having longer on and larger orbitals. As a result of that, there is much space between the electrons, right? Between the electrons, and therefore there is less repulsion. There's less repulsion, and as a result of that, this is more stable. It's more stable. So this is actually the complex. So that's all about the Nephelauxetic effect. The Nephelauxetic effect says that the metallic ion or the free metallic ion is usually unstable due to the repulsion between the orbitals, and when it then form a complex, it is more stable because there is an expansion of the electron cloud or the electron orbital. Therefore, there is less repulsion between these orbitals. Then what is then the difference between the spectrochemical series and the Nephelauxetic series? Now, the key difference between the Nephelauxetic and the spectrochemical series is that the metals in the spectrochemical series are arranged in order of ligand splitting value, while the metals ion in the Nephelauxetic series are arranged in increasing order of Nephelauxetic effect. So that's the key difference. The key difference between the spectrochemical series and the Nephelauxetic series is that metal ion in the spectrochemical series are arranged in order of ligand split value, that is the oxidation state, while the metal ion in the Nephelauxetic series are arranged in increasing order of Nephelauxetic effect. So that's the major difference between the Nephelauxetic series and the spectrochemical series. So with this, I've come to the end of this part. Watch out for the other part. Remember, if you have any question pertaining the course, try and drop it in the comment box down below. And don't forget to subscribe. Thanks for watching and see you in the next video.